Yang, you want a screen share?
Yeah, thank you very much. Does that work?
Yes.
Great, should I start?
Yes, please.
Well, thank you very much for having me, and it's great to see so many friendly faces. I'm going to tell you a little bit about I'll mainly talk about this recent paper that I wrote with Shailesh and Zaid. And I'm putting this in big, bold red because Shailesh really took the lion's share on this project, and he's a really wonderful guy. So let's just begin with a little bit of a review. It's clear that one of the biggest theoretical challenges to string theory is a lack of a selection criterion, or and related to this, a lack of a metric on the landscape of possible vacuum configurations to string theory. And of course, this was realized way back with Mike, who gave this wonderful talk just 5 minutes ago, where he was trying to put statistical measures on the space of possible vacuum. And then, of course, you know, numbers like 10 to the 500 started seeping into not only the theoretical physics community, but into the public imagination. And of course, this is now even more improved with the advance of F theory and so on. You know, the 10 to the 500 is now becoming 10 to the 10 to the very large number. The basic reason for all of this proliferation of possible solutions to vacuum of string theory essentially comes down to the fact that, you know, combinatorial geometry tends exponentially. You know, whenever you have a geometrical structure that is inherently combinatorial, you have an exponential growth. So for example, the most famous data set in string theory is this Kreuzer-Skarke data set of Calabi-Yau hypersurfaces in toric varieties. And these toric varieties are constructed by the theorem of Borisov and Batirev to be from reflexive polytopes. I mean, it's a simple problem. It's just how many integer polytopes are there up to SL2n in dimension n, such that there's a single interior lattice point which can take to the origin, and such that all bounding faces are distance 1 from that. You know, it's a problem you can say to high school student. And yet this sequence is one of the most remarkable sequences, is that we have no idea, right? You know, 1 is in dimension 0, in dimension 1, in dimension 2, there are 16 of these up to SL2z. Already in dimension 3 this 16 was known to the Italian school of geometry, like the Pezzanfano knew about this, but the next numbers are known, and it really required this brute force approach of Kreuzer-Skarke, and the next numbers already unknown, right? So, and this is just to emphasize this, that the actual number of Calabi-Yau manifolds in these is much higher. So we did an early estimate on just brute force it with up to H11 equal to 6, and this is very interesting because we applied for a you know, Microsoft grant, the best cluster at the time of 2014, and we could only go up to H11 up to 6. The point is that to each one of these toric varieties, you need to triangulate in order to get different, right? Each triangulation could give potentially different chunk classes. They all share the same Hodge numbers, but it could much higher. And then this recent beautiful work of these guys estimated the number of triangulations goes even more than that. So even within the Kreuzer-Skarke data, this often quoted 500,000 manifolds for dimension 3, the actual number should be much bigger than that. So there is this proliferation of vacuum degeneracy. So, okay, fine. You say, well, you know, maybe most of this will just give us like random stuff. It doesn't really give us the standard model. But even if you put constraints of the standard model, like this earlier experiments that was done with the Penn Oxford group, and then with the Munich group, you know, it roughly cuts down in about 1 to 10 to the 9th-ish. If you want to just put, you know, basic standard model particle content. Of course, we don't know how to compute Yukawa couplings. I hope my friend Anthony Ashmore will talk a little bit later. In order to compute this Yukawa couplings, you need more, you know, you need metrics and so on. So with the lack of selection principle, you know, this brute force can really do so much. And even if it does so much, it can only cut it down by so much. And I love this wonderful, you know, this is one of the pleasures of working with Philip Candelas. You come up with really wonderful words like triadophilia, the love of 3 generations. And another word I have absolutely no idea about until Philip tells me what it means. Des-res is apparently an English word for desired residence. It's a sort of thing you put in 1960s newspapers for where you want to be. So the standard model is a des-res within the space of actual string theory. And even that's only 1 to 10 to the 9th. And in the space of 10 to the 10 to the something, it's only very, very small. So, and you know, recent estimates, even on the number of standard models, exact standard models based on this heterotic line bundle stuff that Andre Lucas has been leading. And you know, you get a mole of models, right, from Sissies, and maybe even more from the KS, and Jim and friends have done estimated 10 to the 15th F-theory standard models. So as string theory enters the machine learning era, so as Mike said, you know, this is the 4th meeting now for string data. It's kind of wonderful. And it kind of, for us, it started in 2017. This community started in 2017, which is very appropriate because that was the same year that Sophia from Hanson Robotics, like, officially became a human citizen. Like, this person now in the country of Saudi Arabia has human rights, which I think is quite remarkable. So 2017 is a good year. So given this paradigm of machine learning, it's natural to see, you know, what can we do with such proliferation of data, right? So that brings us to oh, very good. Ava asks a wonderful question. I have no idea. Let's chat about that later. I have no idea. I hope so. I hope so. In fact, I hope everybody in Saudi Arabia can drive one day. But so this brings us a paradigm which is called one-shot learning, and this was promoted by Fei-Fei Li at Stanford back in 2002. So this is a very interesting analogy you want to draw. By the age of 6, you know, a typical human child has learned 10 to 30 times 10 to the 3rd object categories. And this is not done by sampling, you know, like 10% or 20% or 80%, as we usually do in machine learning, of each category. There's just simply not enough number of hours of the day for a child to do that. So how does the human mind actually do one-shot learning? Well, you couldn't possibly have done this by supervised learning. As I said, it's usually by 20-80 split or 80-20 split. And this is done by this paradigm called knowledge transfer. You know, for example, having seen a lot of horses and a single bird, the child would recognize immediately that a chicken, whom the child has never seen, is closer to a bird than a horse. So somehow there's been a transference procedure. And so in most cases, a single representative in a category suffices. So this is called one-shot learning. And if you do a couple of them, instead of like the usual 80%, and that's called few-shot learning. So it's natural to ask the question, can one-shot learn such proliferation of data, this mathematical data of string theory, or at least in the worst case, do few-shot learning? And so, okay, just to give a bit of a methodology on how this is normally done, and this is usually done by what's known as a Siamese neural network, or SNN. So what it does is, it's called Siamese because it has 2 twins. It has a pair of twin architectures, and this is completely replicated, and they go through some standard loss function. So you have these are called features networks, or FN, and you have paired of these feature networks, which I'm going to talk about in a minute. But then what this loss function does is to do a contrastive loss of these 2 twins. So for example, you can take like the maximum of some distance, like a typical distance. So in our case, and it's also in the case of usually done by Siamese networks, this features network is essentially some kind of geometrical representation of the data input, and then you map this to Rn, for example, and use your Euclidean distance as part of this. That's why I use this this measure. This is a standard thing, and you can even make it into R3 just because you can visualize that. So then what this features network should do is to have an anchor point for the class. This is the one shot of the class. And then you want to have an idea of what is close by and what is far apart, right? And then this twin network, this Siamese network, then should compare and contrast this by this contrastive loss and spit out a similarity score between your inputs, in the sense that if 2 things are identical, they're similar. If they're not, they should be as far as possible. So let's go back. So now let's try to apply this to the landscape. So obviously we're going to do this to the Kreuzerschkake at some point, but let's do another one that's very much in the imagination of this community, which, very interestingly is the first, as far as I know, the first data set in algebraic geometry. This was done by Candelas and friends. And this is the SISI data set. I think everybody's in this community is familiar with it, but basically for the students, this is just a configuration matrix where you take products of PNs and you take hypersurfaces of multi-degree. And this is complete intersection. So this is the complete intersection criterion. And the vanishing of the Chern class gives is this row sum criterion. I'm going to give an example in a minute. And then of course you say, well, they're all different sizes. So you can uniformize this configuration by various techniques. For example, you can do -1 padding. You can do wrap padding, meaning -1 padding means like you make all in the same n by n matrix, but with -1s because these are degrees, so -1s don't mean anything. You can do wrap padding by simply like tiling a simple size, or you can even do bilinear interpolation, meaning that you can take a 3x3 case and then just linear extrapolate to like a 28 by 28 size one, just to make a uniform. And we've tried all three, and it's kind of interesting to see that these three have given roughly the same kind of behavior. And I like this bilinear interpretation idea, which Shailesh originally suggested, because back in the day I was doing like -1 padding, but you could bias it by picking out favorable ones in which H11 is the same as the number of columns. But if you do this bilinear interpretation, it smears out and that information is completely lost. So as I said, the SISI3 data was done by Candelas and friends in the late 80s. And you can refer to Hubsch's BIS theory for a complete story about this. And this has already been done with lots of nice supervised machine learning experiments by various, I think the state of the art in the supervised learning is done by Urban Field Antenna, where they get 99.96% accuracies on H1 score. So these are on the H11 values of the Hodge numbers. So roughly here, you have 7,890 configurations where your H11 goes from 1 to 19 and H21 goes from 15 to 101. And the ranges for these matrices, as I said, goes to 1,1 to 12 times 15. This 1,1 is, of course, the famous quintic. It's the only one that's a 1 times 1 matrix. Is the 5-4 configuration. And another wonderful set was classified by Gray, Haupt, and Lucas 20 years later. And this one is a much larger data set. So this is the SISI4 data set. I mean, of course, if this goes on, you can do SISI5, SISI6. And again, the growth rate of this number will also be very interesting. This sequence should also be OEIS, and we have no idea what the next number is. But this gentleman classified this beautiful thing, and this comes to be a million. So this is a nice, sizable thing to play with. It's not like 10,000, nor is it as crazy as 500 million, but it's a nice playable size of about 1 million. So we tried some early ML experiments with Lucas, and also Urban Field Antenna and friends also did some supervised learning of Hodge numbers for these. So the Hodge numbers here now are much more wild. H11 is not as crazy. H21 is a bit more spread, and of course there's H31 and H22. Look at the size of H22. It goes into the thousands. And of course, for Calabi-Yau threefolds, H11 and H21 give that's the unique pair that you can have. For threefolds, it turns out there are more constraints. There's another nonlinear relation. So the H11 and H21 and H31 is sufficient to specify. So here, again, the 1-1 goes up. This matrices are 1-1 that goes up to 1620. So the 1-1 is the sextic in CP5. So that's the analog of quintic in CP4. So that's the data set you want to play with. So as I said before, so of course we have a labeled data set of this type and of this type. So now it's the data set into its millions. So it's kind of a nice sizable to play with. And the similarity score, of course, is say if you take say H11, which is one you can focus on, it's the same if the configuration if and only if the H11 is the same, you will get a similarity score of 0. So now the reason I wanted to emphasize that these matrices are like that the sissies are nice because they're matrix representations, right? So whenever they're matrix representations, you can just represent them as pixelated images, right? So that's kind of, you know, the standard thing. And then you can use your standard convolutional network as your features network. So the one that we used here, when we tuned a couple of them, but here is one that you know, the standard convolutional network, as if you're recognizing each sissy as as an image, and you're just classifying the image to its recognition of its Hodge number. All right. So let's just, so that's it. So that's the methodology and the data set. So let's just apply it to our favorite Siamese neural network, which is, I mean, this is wonderfully implemented on Keras. Unfortunately, the implementation of this on Wolfram Alpha, or sorry, on Wolfram Mathematica is not so convenient. So somebody should code this out in Mathematica so that we will play with it. So we took 3% of CC3 and now 0.6% of CC4. These numbers come just because you want at least a couple of representatives in each class. So just to emphasize this, and in this 1 million configurations distributed, say, over 24 classes. Some of them are more, some of them are less. I should have included the plot of the distribution. In the few short class ones, you want to at least have a couple. So there is one large class of H11 equal to like 7, which is at the peak of the CC4 distribution, in which there are like at least 10,000 or 100,000 representatives in that class. So it is sufficient, I want to emphasize, because of the Siamese network, it is sufficient to look at only a less than, you know, on the order of tens to hundreds out of hundreds of thousands to extrapolate this data. And then you run through this with the Siamese network with a standard Adam and learning rates. So here I want to emphasize are the plots. So here are the, so this is the 19 classes of H11 for CC3 and the similarity score as detected by the Siamese network, having seen only a few shot learning of this. And you can see that this is, it's very much blue on the diagonal. And this is C4. This is much more, this is a much more ambitious thing, which is you're looking at 1 million of them and you're looking at only hundreds of them. So this is less well behaved than this. I should have quoted the actual accuracies, but I'll show you a plot that will that will represent everything, which is this thing. So this is a wonderful diagram that you can see. So what we've done here is that you can explicitly see the representation of the data. So what the Siamese network has done is to assign the similarity score to each manifold having only looked at its pixelated image, and it's split into the 19 categories of its Hodge number, the H11, and by similarity score clustered according to this behavior. So this is a very beautiful way of seeing 8,000 different manifolds, and you can see different colors clustered differently according to H11. You would expect this because, well, you wouldn't naively expect this because computing H11 from a configuration is not so easy, right? And especially if you used, as I said, linear interpolation, because that washes out any favorability condition. So you're really looking at like normalized, stuff, and it just looks like blobs of images, and yet they cluster so beautifully according to Hodge number. And we've done this in a representation to unit sphere just to make it even more visual. So we clustered not just to R3, but we actually map it onto the unit sphere in R3. So you can see how the different sissies cluster in this way. And you can see a similar behavior with CC4. Now this is 1 million points, having seen only a handful within each H11 in 24 different classes. And you can see the clustering of different H11s according to this shape. So this basically, it confirms what one always would imagine, what I've always imagined, and I guess what Mike was mentioning earlier, is that mathematical data should have structure. We may not know what the structure is, but if you pass through this, you should have some kind of recognition. So this is a good way of formulating, this is a good way of conjecture formulating that configurations of algebraic varieties should cluster in this way. And I think this is a generic feature in algebraic geometry. So yeah, you can do a little more. You can do a little more with this. So I mean, you can zoom on to a particular H11 and then try to see whether there's a sense of typicality. So here's a H11 cluster taken from this CC3, and you zoom in and you take the H11 equal to 7 cluster, and then you try to do k-means clustering of the complex structure, which has a much bigger variation, and it detects different clustering behavior there. And in this sense, it gives a good measure of what a typical complex structure is of H1 or something. I've given a concrete example, but of course, this is a proof of concept of what one can do in general. Distributed contracts in the network. Sorry?
5 minutes.
Okay, cool. And in contrast with the supervised clustering in this nice network. So just let me conclude, but I have 5 more minutes, so I can give you 2 more minutes to go for something completely different. It's like what do you call Monty Python moment. So of course, this idea of few-shot learning should be, we've used as a proof of concept for 1 million manifolds, but I think this should be extended obviously to like concrete standard model thing. If you can make whatever your string standard model configuration into what it is, and there's like a large proliferation thereof. And I think this few-shot learning does actually give at least a handle of possible selection criterion just by the virtue of similarity score and by a distance measure, which in this case is the geometrical distance measure being mapped to the landscape. So if you would indulge me in 1 more minute, here, just because I have here now for something completely different. And this is, I'm really, really happy that Mike had a slide on elliptic curves, because that's my other deep, passionate love. It's another fun landscape, which is not the string landscape, is that of arithmetic geometry. So we played with various versions, ranging from descent d'enfant to elliptic to Sato-Tate conjectures. But the one that really sits at the depth of my heart is the Birch-Swinton-Dyer conjecture. So can one learn machine learned aspects of the Birch-Swinton-Dyer conjecture? So this is an experiment that I did with this card-carrying number theorists. I just want to give you a 1 minute report on this. So I won't get into the details. So here's a wonderful data set of about 3.5 million elliptic curves. And this is the strong version of BSD conjecture, where there's 7 quantities, of which the Tate-Shafarevich group is the most difficult that people know of. So is it true that by correct representation of elliptic curves, one can machine learn this in the standard supervised learning method to predict the rest of these quantities, and detect that the Tate-Shafarevich group is indeed the hardest quantity? And indeed, to a long story short, that is indeed the case. So it's wonderful that Mike anticipated this experiment in his last slide. Detecting rank 0-1 due to the result of Bagavar and the conjecture of Sarnak, indeed, you would expect 0-1 split at 50% and that is indeed true, even by logistic regression. And then you can do other things like, well, I won't bore you with this, but the Tate-Shafarevich group, you can break your neck. You cannot find a good machine learning algorithm that can do better than, almost random guessing. So that's kind of really nice as a confirmation that, there are certain data sets which behave as hard data sets. And if you can break it, then you can probably break every bank in the world. So that would be really wonderful to know. So with that, I'll end here with 2 different landscapes. Thank you.
Yang? Questions? Sven?
Hi Yang. Thanks for the talk. So first question is methodological. In the sense of, I think it's very important to build in all the biases that we know. So in particular, all the symmetries of the CCs.
Yes.
So the question comment is, I'd love to see the results when you apply graph neural networks on this to see whether that pushes the performance significantly. And the second one is on the large numbers, because I think we there are other areas where there are large numbers. If you just think about combinatorial possibilities, say arising in the Ising model or so.
Yeah.
So have you got a comment on, comparing the landscape sizes that you're mentioning to such combinatorial options that arise in other areas of physics?
That's a good question. So for the first comment, thanks for that. I think actually interesting. I think of all of these experiments that have been various done over the years, I think you built in like a lot of the symmetries, more than just the naive permutation symmetry. We haven't done it in our experiment, but certainly we should. I mean, especially like you should build in like even more subtle symmetries like split symmetries, right? Stuff like that into it and see whether that's a much more subtle a thing for the machine to detect. And that's essentially what we're doing. So thanks for that suggestion. And the other one, I think I don't know, I'm an extremist. So I think everything comes down to combinatorics. If there is a proliferation of data, no matter what subject it comes in, it comes down to some kind of an underlying combinatorial problem which kills you. So I think the string landscape is there in every single proliferation of the string landscape problem. Is there some combinatorial underlying combinatorics, whether it's number of graphs or whatever, that just grows exponentially. So I think it would be actually really nice. I think what my student Ellie is actually trying to use GNNs, graph neural networks, to try to sort out some of this. I think that should even go into the I think if I understand your suggestion correctly, that should even be built into the features network in this case, right? If I have some kind of a combination of CNN with GNN, yeah, that should to stay tuned, and hopefully that will improve. Yeah, absolutely.
Tim?
Hi, great talk. Thanks. Thanks a lot. It was great to hear about this. I noticed the paper and I realized that I could just wait a few weeks to hear the talk.
Yeah, this is what we're doing. That's what's been there.
Yeah. So I'm extremely sympathetic to this idea of trying to use ML to distill sort of common information out of string vacua. Someday, as a community, we're going to have to put cosmological dynamics on this if we want to talk about vacuum selection. Have you guys thought about how your distance metrics may or may not make sense if you were to put decay rates into the game, or in principle move to a point where you stabilize moduli and compute decay rates and things like that?
I personally have, maybe Shailesh has, if you see the audience. I would, yeah, I mean, it's certainly something to try. I'm just a little worried about if you start putting these constraints in, how much more would the features, the input features would be. If you want to start putting in not just manifolds, but manifolds with, other information. I guess if the thing is still representable as some kind of a tensor, I guess why not?
Yeah, I guess in some sense, I'm just asking like these non-dynamical things, relationships that we learn between the data. When we actually want to put dynamics on it, how much of it? How do we put those things together? It's not that I have a good idea yet myself, but
that's a good point.
I'm curious because vacuum selection has to be dynamical, right? It's cosmological.
Absolutely. See, that's a very deep question. Your question is like how close is dynamics to algebraic geometry, and right? In some sense. Because the fact that all of these different architectures have worked from CNNs to SNNs to whatnot on this problem of configurations in algebraic geometry, because every algebraic variety can be represented in this way, or at least every projective variety can be done this way, and then so there's some underlying matrix structure which makes it very, very structured. And so your question is, at some level, it's like if you put dynamics, if you put differential equations in, would the dynamics mess up this kind of kernel computation?
Well, it's not far-fetched to imagine that there is a connection, because these topological things do have notions of distance between them that might affect the dynamical distances via decay rates or something like that. For example, Calabi-Yau with very different Hodge numbers will require many topological transitions to get from one to the other. But I guess I just don't yet see a general principle in any of the work in the literature, and I don't know.
Yeah.
But
That's what you and I got to work on.
There you go. All right.
Yeah,
I mean, if there's,
interesting to see that. Yeah.
yeah, beautiful talk. Thank you.
Any other questions for Yang? Well, if not, let's thank him again, and then Sven can set up.
Thank you, everyone. I'll stop share.